Alright, hello class. In this video we are going to be looking at just a bunch of examples using the basic derivative rules. Now that we've established all of these basic rules all the way up through the trig rules, now we're just going to look at some examples. So let's just get rolling on them. Alright, let's start by looking at this function. Let's say f of x is equal to 6x to the 5th minus 5 halves x squared plus x plus 5. Alright, so to find f prime, now what I want to mention here is never call, when you take the derivative, f. Never just say it equals whatever, okay? There's a huge difference between the original function and the derivative. Okay, so we need to be really careful about what we call them. Now that might not seem that clear now, but when we move on to the next module, and we start having to plug things into, say, f or f prime to give us different things, then we really need to start labeling them correctly. Okay, so anyway, this is all going to be essentially a sum rule, constant multiplication rule, and power rule, right? So from the constant multiplication rule, the 6 comes along for the ride, and then we get 5x to the 4th here from the power rule. Okay, here the 5 halves is just a constant. It comes along for the ride. And then we have the derivative of x squared, which will be 2x using the power rule. The derivative of x, well, that is x to the 1. And I think we've already established that any linear term, the derivative is just going to be the slope, but if you forget that, this is x to the 1, so you can think of this as being 1 times x to the 0, which comes out to just be 1. Okay? Then the derivative of a constant, okay, and then the derivative of a constant is 0. So I'm just going to go ahead and put the plus 0 here to specify that a constant all by itself, its derivative is 0. Alright, now if we clean this up a little bit, we're going to get 30x to the 4th minus, here the 2's cancel, so we get minus 5x plus 1. Okay, and there's our derivative. Clearly way nicer than using the limit definition with the f of x plus h minus f of x all over x, or all over h, and simplifying that with this monstrosity. Alright, for the next example, let's look at g of x equals 6 square root of x minus 4x cubed plus 9e squared. Alright, so let me show two ways that you might go about doing this. One is you just remember that the derivative of the square root of x is 1 over 2 square root x. Okay, that's probably the easiest way to go. Then we have negative 4 times 3x squared. And here is a trick. You might think, oh, e to the whatever is itself, but this is e squared. This is actually just a constant. Okay, this is one of these favorite tricks that math professors like to throw onto quizzes and tests and whatnot, is very funky looking constants. No matter what the constant is, it goes to 0. Okay, so this whole thing, its derivative will be 0. Alright, so from here we have some simplifications we can do. This will end up being 3 over square root of x, and then minus 12x squared. Alright, so there's our g prime of x. Alright, another way you could go about doing this is rewriting this if you needed to, because you could always rewrite the square root of x as x to the 1/2, then minus 4x cubed plus 9e squared. What I will mention is if you need to rewrite the function, make that a separate step. Don't start mixing derivatives and simplifications together. I see it all the time where some students will start taking derivatives and then they'll simplify and then think they're done and move on. Make it a separate step. Simplify, then differentiate. Okay, because here our g prime, well, we could write this, now we have it as x to some power, and so it would be 1/2 x to the negative 1/2. Shift it over a little bit. Minus, same thing here, we'll just get the 12x squared plus 0, and this will end up being 3x to the negative 1/2 minus 12x squared. These, though they look different, are exactly the same thing, because here you can move this down to be 3 over x to the 1/2, and x to the 1/2 is the same thing as writing 3 over square root of x. Now, most online systems will likely take either of these. In general, my labs specifically will pretty much know both of these answers. Okay. In fact, it'll know a lot of answers provided they are algebraically equivalent, meaning they're pretty much the same thing, just written differently. It will know how to proceed from there. It will know what you're talking about, provided you plug it all in correctly. All right, moving on, let's take a look at f of x equals the square root of x plus 1 all times the square root of x minus 1. Now, there are two ways to actually go about doing this one. One is we could use the product rule, of course. All right, so the product rule, we would do the derivative of the first guy, which would be 1 over 2 root x. The plus 1 will become plus 0. Then we'll leave the second function alone. Then we'll plus the first function left alone times the derivative of this second function, which will be 1 over the square root of x. Okay, and I guess I should put, just to be consistent here, the minus 0. Normally, when I'm working these, I don't often write the plus or minus zeros when a constant goes to 0. But for these early examples, you're going to see me do that, just to be very explicit. And I forgot the 2 there. It's 1 over 2 root x. Okay, and this will end up being 1 over 2 root x. And notice these can just be factored out. Whoops. So, actually, let me just write it like this to start with. Okay, so we'll have 1 over root x times the square root of x minus 1, then the square root of x plus 1 times 1 over 2 root x. We can actually factor out that 1 over 2 root x if we'd like. Okay, and we'll be left with the square root of x minus 1 plus the square root of x plus 1. I'll keep the parentheses to make it consistent, but the 1s are going to cancel, and then we're going to be left with just the 2 square roots on the inside, so we get 1 over 2 root x times 2 root x. Well, look at that. It comes out to be 1. Okay? However, what I will mention is that if you just put this in as your answer, it's likely, unless there's a really strict setting put on, you're likely going to be counted correct here. Okay. All right. The other way we can do this problem is first simplifying f. So f may look familiar, right? It hopefully looks familiar because we've been putting these things together every time we make limits using conjugating factors. This sets up a difference of squares, right? Because it's going to be the square root of x squared minus 1 squared. So this is just going to be x minus 1. And now that we've simplified it to be x minus 1, f prime of x is just 1. Okay? Notice how much easier this was. A lot of times using some algebra first to simplify the function is going to make things a lot easier than just blindly doing the product rule or the quotient rule. However, it doesn't really matter because as long as everything you do is a correct step and logically sound, you will end up with the right answer at the end every time. All right, to give another example of this, seeing this g of x, which is x cubed minus 6x squared plus 8x, all over x squared minus 2x, looking at this, you might think, oh, this is the quotient rule, but there are ways we could simplify this to avoid it. Okay, so let's start by factoring the top and the bottom. We can factor an x out of the top and the bottom, right? So we would get x times x squared minus 6x plus 8 on the top, and x times x minus 2 on the bottom. So the x's cancel. And then similarly, the top will factor further because if we want two things that multiply together to give us 8 but sum up to be negative 6, we could factor that into x minus 2 times x minus 4 because the negative 2, negative 4 will give us positive 8, but the minus 2, minus 4 will give us negative 6. And so we get nice cancellations here so that this function comes all the way down to be 4. Now, when we do this at each step, here we're saying that x is not allowed to be 0. Well, that's true anyway because that's going to cause 0 over 0. And here we're saying that x can't be 2, which again, that causes 0 over 0. So those are already things that can't be in the original function anyway. And so now g prime of x is just going to be 1. Way easier derivative, but we had some algebra to do firsthand. If we tried it just using the quotient rule, okay, well by the quotient rule, just straight from the quotient rule, we have the derivative of the top, which is 3x squared minus 12x plus 8 times the bottom left alone. Now we got to be careful with our parentheses here. So here's our top derivative. Here's our bottom left alone. Then it will be minus the top left alone. Okay. Times the derivative of the bottom, which will be 2x minus 2. Okay. All over the denominator squared. So we'll have x squared minus 2x squared. Okay, so this is here, the top left alone. This is the derivative of the bottom, and this is the bottom squared. All right, this doesn't look promising. Okay. Right, really at all. However, with enough algebra, we can actually get this to be 1. I'm not going to do that right now. I just want to show that don't be so quick to jump straight to a quotient rule or product rule. You might be able to simplify some things before you get there. Of course, that's not always the case, right? Say here, if f of x is equal to e to the 3x all over x squared plus 1, there's no real algebra we can do here to simplify this. We just have to use the quotient rule. And I know we need to use the quotient rule because, well, I have two separate functions dividing one another. Therefore, f prime of x will be the derivative of the top, which will be 3 e to the 3x, times the bottom left alone, okay, minus all the top left alone, times the derivative of the bottom, which will just be 2x, all over the denominator squared. Now, here's the beauty of this. So let me just write this as top derivative, the bottom left alone, minus the top left alone, times the bottom derivative all over the bottom squared. Okay. Here's the beauty of this, though. Unless some really strict requirements are set, you can actually plug the answer in just like this. Okay. Don't feel like you need to simplify this much further. In fact, I always tell my students in my classes, for right now, when we're still just learning the derivatives, you can stop right here. Right? I have nothing against just stopping right here. Mainly because what we're trying to get at right now in this module is, can you just differentiate? Right? I don't care right now if you can simplify. We will focus on simplifying these things later. Okay, the simplifications will be very important much later on. Right now, we just need to learn the rules. Okay, so I wouldn't bother simplifying this. I mean, you can, but, you know, I don't know if it's well worth our time here. All right, so for my advice in this module, when we're just learning the derivatives, just differentiate, move on. Don't focus too much on the simplifications. All right, for our next example, let's look at sine of x plus cosine of x all over e to the x. Once again, there's no real way to simplify this in a meaningful way that will actually help, so we're just going to use the quotient rule. Okay, so g prime of x, well, it would be the derivative of the top, so the top is sine of x plus cosine of x. So the derivative of the top will be cosine of x minus sine of x. Okay, then times the bottom left alone, then minus the top left alone, which will be sine of x plus cosine of x, times the derivative of the bottom. Well, the derivative of the bottom is still just e to the x. Okay, all over the denominator squared. Now, often I don't simplify these, but sometimes you can look at these and see that, well, maybe they will simplify by a lot, and that's sort of what we have going on here, because if I factor in e to the x out of the top, okay, we'll be left with a cosine x minus sine x minus, if I distribute this minus sign, we'll have a minus sine x minus cosine x. So what ends up happening now is, note we have an e to the x and an e to the x squared. So the e to the x here will cancel with one of them here, and our cosines cancel, and we're left with just two sines. So this actually simplifies down nicely to negative 2 sine x all over e to the x. As I said, this is not necessary, right? But sometimes, this is just to show that sometimes these can simplify down by a lot and very nicely. In this module, it's not required, though. All right, so for this next example, let's say y is equal to negative x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x. Now, as written, this is actually not going to be very nice because we're going to have a product rule here, right? Another product rule here, another product rule here, and then this one is just, you know, the constant comes along for the ride. So this is a lot of product rules. I would prefer not to have to do this many product rules, so we can. Feel free to go ahead and do that if you prefer. There's some algebra we could probably do first. In fact, there are a couple of options here. One thing we could do is we could just join up the sines and the cosines and factor them out, and then we would reduce this down to just 2 product rules. Right, sort of like this. I've now joined it to have a cosine term and a sine term. Okay, and so this would just be 2 product rules. And that's probably the most straightforward way to go about this. So we could maybe factor some things some more or try and set up some other bigger simplification, but this is how I'm going to do it. This is just 2 product rules instead of 3, okay? Y prime, we'll do this product rule, so it'll be the derivative of the first, which will be 6 minus 3x squared, times the second left alone, plus the first left alone, times the derivative of the second, which will be negative sign. So instead of putting times negative sign, I'm just going to change this to a negative here and minus sine x. Okay, so here is the derivative of the first term. Okay, for the derivative of the second term, I will do it down here. It will be a derivative of the first, which is going to be 6x. All right, and that constant just goes away. So times the second function left alone, then plus the first function left alone, times the derivative of the second, which will be cosine. All right, and so here is the derivative of the second term. So notice we still did it term by term, we just had product rules within a sum rule. Okay, you're going to see things like that. That's just par for the course, unfortunately. Okay, and we could simplify this down some. You'll notice that you have a 6 minus 3x squared cosine and plus a 3x squared minus 6x cosine. So those are actually going to cancel. Okay. Then we have let me write this out as we have a negative 6x sine x plus x cubed sine x. Then this is a plus 6x sine x. So the 6x sine x is also cancel, and we're left with just the x cubed sine x, okay, which is not too bad. All right, for this next example, let's say we have x minus 1 all times 2x squared minus 1 all over x cubed minus 1. Now, just looking at this, this is a quotient rule with a product rule on the inside, okay, which sounds awful. However, if you're familiar with your more advanced factoring, you might recognize this as a difference of cubes. Okay, so difference of cubes works like this. If you have an a cubed minus a b cubed, it comes out to be a minus b all times a squared plus ab plus b squared. And the reason this works is if you distribute the a across, you'll get a cubed, right, plus a squared b plus ab squared. Okay, then when you distribute the minus b across, you'll get minus a squared b, and these two cancel. Then minus ab squared, so these two cancel. And then finally, the negative b times the b squared is negative b cubed. Right, so that's how, I guess this doesn't need parentheses, that's how an a cubed minus a b cubed factors. And if there's a plus there, all you do is change this sign and this sign, the middle signs. Okay, so this is actually going to factor, and this is the important part because it's going to simplify our lives a lot. And that's one nice thing about algebra when it comes to calculus, is algebra really simplifies a lot of our problems, a lot of our differentiations, and helps us with our later on problems with when we start applying this stuff. Anyway, so this is going to factor this x cubed minus 1 cubed, which is what we have, to a minus b, so x minus 1, all times x squared plus a times b, in this case will just be plus x plus 1. Okay, so these x minus 1's cancel, and now we have changed this problem from a product rule within a quotient rule, right, a double rule to just a quotient rule, which to me, that's reason to celebrate, right? Way less work here. So, well, maybe not in the long run, but yeah, so with just a quotient rule, now we can just do the derivative of the top times the bottom left alone, okay, minus the top left alone times the derivative of the bottom, which in this case will be 2x plus 1, all over the denominator squared. Okay, and there we go. I'm going to leave it like that. Of course, you know, there are cases later on where we'll want to simplify, but we're not going to worry about that right now. We just found the derivative. Of course, we can't always use algebra to get out of some more complicated derivatives. So unfortunately here we have a product rule on the top and a quotient rule on the bottom. So I didn't want to leave you hanging there. I do want to show you how you would approach something like this. But essentially here we have e to the 2x times secant x, so when we do the derivative of the top, we're going to have to do a quotient rule, or excuse me, a product rule, but this is within a quotient rule. Okay, so when we do the derivative of the top, we're going to have to do a product rule. So it will be the derivative of the first, which will be 2e to the 2x, times the second guy left alone, okay, plus the first guy left alone, times the derivative of the second guy. And the derivative of secant is secant x tangent x. Okay, so this whole thing right here, this is just the derivative of the top. Okay, then we'll multiply by the bottom left alone. So this is just the bottom, minus now the top left alone, times the derivative of the bottom, which will just be 2x. And this whole thing all over the denominator squared. Okay, so here is the top left alone, and here is the bottom differentiated, and this is the bottom squared. Okay, and as I've said before, we can just leave it like this. All right, just plug that into our MyLabs, or on paper, on a quiz or a test, if you're doing it in class face-to-face, you can just leave it like this and move on. I don't require simplifications yet. I think I'm starting to sound like a broken record here, but I swear I say this 1,000 times, and yet so many people don't believe me. I'm serious. You can stop here in this module. Okay. Now, if we wanted to simplify, there's one major way we could, in that every piece here shares e to the 2x secant x. So we can factor that out and actually make this look quite a bit nicer, because we'll have the e to the 2x secant x sitting outside, and then we'll just here have a 2 plus a tangent x, and this all times this x squared plus 1, and here just minus the 2x. Okay, so it still might not be, you know, gorgeous, but it's a little cleaner. Okay, now one advantage to simplifying is the more simplified the function is, and this is just when we're talking about plugging it into the MyLabs. Plugging into MyLabs is going to be easier, right? Because you have less places to make mistakes when you're plugging it in directly. Also, if you need to, say, go any further, if you need to take another derivative, right? If you need to take a derivative a second time or a third time, getting it as simplified as possible is going to be really beneficial there. But in general, I'm just looking to see if you can differentiate. All right, let's look at another example. Let's say f of x is x squared plus 1 all over x times cotangent of x. Now, as written, this is a quotient rule within a product rule, right? But I feel like we could actually change the way this looks. Since this is just being divided by x, what we can do is just like split the fraction up as x squared over x plus 1 over x times cotangent of x. All right, and you might be thinking, well, now we've just created two quotient rules. However, if we don't forget our algebra here, x squared over x is just x. 1 over x we can write as x to the negative 1 and use the power rule. Okay, or I think some of you all probably just know what the derivative of 1 over x is, but if not, we can do this, and now this is just a product rule. All right, we don't have to introduce the quotient rule at all. So f prime will be the derivative of the first guy, which will be 1, then minus x to the negative 2. So remember here, you bring the negative 1 down, so that makes it a minus 1, and then it's negative 1 minus 1. I know we're so used to just reducing that number, but keep in mind if you have a negative exponent, it's going to look like it's going up. Okay, so here's the derivative of the first guy times the second guy left alone plus the first guy left alone times the derivative of the second, and the derivative of cotangent is negative secant squared. Or sorry, negative cosecant squared. Okay, so I'm just going to write this like this. All I'm doing here is moving the minus here. All right, and that's it. We have 1 minus x to the negative 2. Yes, you can leave it like this. Okay, or you could rewrite it as 1 over x squared, but I don't see a need to do that. Okay, you can leave it like this. Times cotangent x minus x plus x to the negative 1 times cosecant squared x. All right, so the moral of the story here is always be on the lookout for some algebra that might simplify the problem first, then start trying to differentiate. All right, let's look at this example. Say we have 1 over cotangent x all over 1 plus cosecant x. This is, of course, a quotient rule. Thankfully, it's not a combination, it's just a quotient rule. So f prime of x will be the derivative of the top. So remember, the top always goes first. So the derivative of cotangent is going to be negative cosecant squared x. Then times the denominator left alone. Okay. Minus the top left alone times the derivative of the bottom. So the derivative of the bottom, 1 plus cosecant x. The derivative of cosecant, well, first of all, the derivative of 1 is 0, so we can just drop that. The derivative of cosecant is going to be negative cosecant x cotangent x. Okay, and this whole thing will be all over the denominator squared. And as I've mentioned before, multiple times now, of course we can just leave it like this and move on. All right, so for our next example here, let's look at the function y equals tangent x over secant x times e to the x over 2 times the square root of x. Now this is a big old product rule. We're going to have a quotient rule in the middle of it, well, really at the beginning. Okay, and however, what I'm going to do is see if I can simplify this so that maybe I'm not doing a quotient rule within all this product rule stuff. So over here, tangent of x over secant of x, well, if we remember that tangent of x is sine of x over cosine of x, and secant of x is 1 over cosine of x. When we divide these two fractions, we're going to invert and multiply and get sine of x over cosine of x. And then when we invert this, we'll have cosine of x over 1. So this can actually simplify down to be sine. Right? So I'll have sine of x times e to the x over 2 times the square root of x. And now this has thankfully been simplified down to just being a product rule. Okay, and so a product rule with 3 parts, well, you just have a product rule with 3 parts, right? You do the derivative of the first guy, so derivative of sine will be cosine. Then you leave the next 2 alone. Okay. Then you leave the first guy alone, and you take the derivative of the middle piece. So x over 2, that's the same thing as 1/2 x. So this is going to be 1/2 e to the x over 2. And then we leave the third piece alone. And then finally, we'll leave the first piece alone. We'll leave the second piece alone. And then we'll take the derivative of the third piece, which will be 1 over 2 root x. And there we go. All right, so I think from here, I find the trickiest part for most people is knowing which rules to use. So always be on the lookout for quotient rules and product rules. Okay, always be on the lookout for simplifications to simplify it down to something like we did just here, where, okay, instead of a quotient rule with a product rule, now it's just a product rule. Okay. And then from there, it's just knowing all the different basic rules, right? It's just knowing, well, the power rule isn't too bad. The e to the stuff rule isn't too bad. It's, I think, a matter of just knowing all your trig rules. Which again, if you know, say, 3 of them, you kind of have all of them, if you don't remember them. Okay, so I'm going to leave it here. This should get you rolling on the homework, hopefully. Again, we don't have enough time for me to show you every single possibility that you'll ever come across, but I think this is probably a good look at the overall strategies for approaching these. Okay, so with that, I will end it there and catch you all in the next one. Cheers.